So this is a problem in which the goal is to multiply one polynomial by another polynomial. The first polynomial here, the first factor, has 3 terms in it. The second factor has 2 terms. So terminologically, we would call the first factor here a trinomial, 3 terms, and the second factor here a binomial, 2 terms. And so it's the first example on this page, anyway, of a product that has an unequal number of terms in one factor as in the other factor. Now, secretly, there is an example like that on the previous page, but you have to look at number 2 to find it. In number 2, you're multiplying a pair of polynomials. The first one of them has 1 term, and the second one has 2 terms. But admittedly, that's cheating a little bit, because that one's definitely more straightforward, because one of the polynomials rather only has a single term. So there's certainly more going on in number 7. So how did you approach this problem?
Well, left and equal said it was easier to flip the 2 to the front and then do the multiplication.
Okay.
The 6b to the 7.
So one thing you could do, if it makes it easier to read, is to reverse the order of multiplication. Put the 6v plus 7 in the front, and the 4v squared minus 5v minus 2 at the end, and then multiply it out that way. If that makes it easier on you, by all means. And then once you've written it that way, what did you do? Multiply. And what did you multiply by what? Maybe what was the first thing that you multiplied?
6b times 4b squared.
Okay. So the first term of the first expression multiplied by the first term of the second expression. And then after that, what did you multiply?
Times the 6b times the -5.
Okay, first term from the first factor times the second term in the second factor. And then if I can hazard a guess, your third multiplication was 6v times -2. Okay, so that takes care of the multiplications of 6v by all 3 of these terms from the second polynomial. And then after you did those 3, what else did you do?
Same thing with the 7.
Same thing with the plus 7. So the plus 7 multiplied by the 4v squared, the plus 7 multiplied by -5v, and the plus 7 multiplied by -2. That takes care of multiplying the 7 by all 3 of the terms in the second factor. And that should do it, right? If you carried out all of those products, you end up with a total of 6 different terms at the end of that process. And then there might have been some terms in that mixture that were like terms that you could combine and simplify your answer. So that will work. That'll work just fine. That's what the authors of our other textbook would call the horizontal method of multiplying one polynomial by another. And it's just an extension of what's the simpler rule that works for you in a question like number 5 at the top of the page. What do we call the rule that we would apply to something that looks like that? I saw it written on a few of your papers. What name do we give to the technique? FOIL. So FOIL is the particular acronym given to the case of multiplying one binomial by another binomial, right? 2 terms in the first factor, 2 terms in the second factor. And it has the same effect, right? We end up multiplying each term from the first factor by each term from the second factor, and then combining the like terms to get to the end. FOIL, of course, standing for firsts, so the product of the first term and the first term. The outers, the first term in the first factor times the second term in the second factor. The inners, the second term in the first factor times the first term in the second factor. And then the lasts, the second term in the first factor times the second term in the second factor. It's a mouthful. Really, the shorthand way of saying it is we need to make sure that everything from the first factor multiplies everything from the second factor. And so in the case of 2 factors in the first and 2 terms in the first and 2 terms in the second, we end up with a total of 4 terms after we do all of this multiplication, because it's 2 times 2. Once we take care of all the terms in question number 7, how many do we expect to get? How many terms should there be? So there were 3 terms in one of the factors multiplied by 2 terms from the other. So the number of terms that we'll expect to get, yeah, that's one way of knowing that you've accounted for every possibility, right? That you didn't accidentally miss one. If I'm multiplying something with 3 terms by something from 2 terms, I'm going to need to get 6 terms along the way, right, before I combine my like terms and simplify my answer. So that's one way of knowing that you've gotten them all. But I wanted to propose a couple of alternative models besides the one that I've sketched here that might help you to do, I don't know, smarter bookkeeping on these multiplication problems. The first is the so-called the vertical method again. I want to make the analogy here of how do you multiply the number 452 by the number 67. What do you end up doing when you multiply these two numbers together?
Multiply 7 first.
Okay. So first thing you would do is take the 7 and the 2, multiply them together, end up with, what, 14? I'm going to skip the whole carrying part, even though that's a large part of the story when you learn how to do this in elementary school or whatever. But then the second multiplication you end up doing is the 5 times the 7, right? Which is going to give you 35. Again, I'm skipping all the carrying, which is something you would never do if you were actually trying to multiply these numbers out. And then after that, the 7 and the 4 need to multiply. That's going to give you 28. And then once you've multiplied the 7 by all 3 of those other digits, what happens after that? Right. So multiply the 6 and the 2, and we get 12. But then because the 6 was actually a tens digit, we end up writing that 12 in the space underneath where we had the product of the other tens digits with ones digits. Right? And we leave this empty space sitting over here, either with an x in it or maybe better with a 0 in it or something like that. Right? So the 6 and the 2 multiply, and then the 6 and the 5 need to multiply, give you 30. And finally, the 6 and the 4 to give you 24. So in other words, you end up doing the product of every digit from one number and every digit from the other number. So if I have a 3-digit times a 2-digit, I end up with 6 multiplications that I do along the way. And once you do all those multiplications, what's your last step? If you're multiplying 2 multi-digit numbers together. Yeah, the last step is an addition step. And there, because of the way we've written everything, everything lines up above its place value, its correct place value, and so we end up adding together 58, 24, whatever. So this is a version of, this isn't the right answer down here at the bottom because we didn't do any of the carrying. Carrying is the one thing that makes digit arithmetic kind of irritating. What I really wanted to focus on was just the process, multiplying every digit from one by every digit from the other, and then adding all the results at the end. Because we can apply that same process to this problem. Let me make some space here. And use that same vertical method to multiply 4v squared minus 5v minus 2 times 6v plus 7. So what do you want to do first? Yeah, negative 2 times 7, sure. That's going to give me minus 14. And then after that, maybe we'll reach for negative 5v times 7. What's that give you? Negative 35v. And then 4v squared times 7. 28v squared. And now we've done everything that we need to do with 7, so we'll move on to the 6v. What do you want to multiply that by first? Yeah, how about the negative 2? So that what we end up with is negative 12v, which we have to write underneath the negative 35v because it's a like term to it, right? So moving over a space the way that we do in the digit algorithm makes even more sense here, because we can see visually that that's a like term. It belongs with the other one that has a v in it. And then 6v times negative 5v, this pair. What does that give you? 30v. Negative 30v squared, right. So now we're starting to get into examples where, because we're multiplying different powers of v together, the exponent properties come in and apply. What are the exponents on these v's here? 5v is v to the what power? Remember, a variable by itself is the same thing as that variable to the power 1. And so if I multiply v to the power 1 by another v to the power 1, how many v's do I end up with? Because we're multiplying these powers, the exponents add. Right, so this is the only time that you change exponents, is when you're multiplying powers of a common base together. Right? When we were doing like terms, exponents didn't change, because denominations don't change. But here, they do change when we multiply them together. For the same reason that the 6 and the 5 in our digit example over here, even though they were originally tens digits, when we multiply them together, we get something which belongs as a hundreds digit. Right? Because 60 times 50 is not 30, it's 300. Right? So changing place value and changing powers of v or x or whatever happen for the same reason. And exponents change when you multiply powers together. So then the final product that we need is the 4v squared times 6v. And what does that give you? 24v to what power? To the third. Right. Because we have a first power coming from the 6v, a second power coming from 4v squared, and the exponents add 1 plus 2 to give us 3. So now we did all the multiplication. How do we finish? Adding. And because we've lined everything up in this nice vertical format, we can see what goes with what. Negative 14 has no match. Negative 35v minus 12v is negative 47v. This method also helps to prevent mistakes in adding like terms, because we don't change the place value, if you like, of the terms when we add them together. 28 of them minus 30 of them, negative 2v squared, and finally 24v to the third, which I believe was the answer that was on the answer sheet. So that's one other way of sort of bookkeeping for a problem where we're multiplying one polynomial by another. So here's one more approach to multiplying one polynomial by another, and this one is going to be useful for the very last one that we talk about, which is question number 6 on here. And here the method involves just drawing a little table. In this case, it's going to be a table with either 2 rows and 3 columns, or vice versa, whatever connects better for you, whatever you prefer. And the columns in this example are going to correspond to the 3 terms from my first factor. So 4v squared is one column, minus 5v is another, and then minus 2 is the third. And the rows, of course, are going to correspond to the other factor, the terms of the other factor. So 6v, the first row, negative 7, the second row. So how does this help? Well, again, we have 3 columns and 2 rows, so we have a total of 6 boxes to fill. Each box is going to get the product of the corresponding pair of terms. Right? And filling every box makes sure that you've gotten every product that you need to get. So we'll just go through and do the multiplications. Maybe starting down here, negative 2, sorry, I didn't want a minus 7 here, did I? Plus 7. Negative 2 times positive 7, negative 14. Negative 5v times negative 7, negative 35v. Negative 5v, sorry, 4v squared times 7, 28v squared. And continuing on, negative 2 times 6v, negative 12v. Negative 5v times 6v, negative 30v squared. And then 4v squared times 6v, 24v to the third. So there's all 6 of our terms. By the way, those are exactly the same 6 terms that we saw over here on the left when we did it in the vertical method. Just kind of arranged in a different order, but they're all there. And now all we have to do is add all the terms that we see in these boxes. And by virtue of the way we've arranged it, the terms that are like to one another actually appear on diagonals in this example. So, if you like, where we find them is here, here. That didn't show up so well. Try that again. So here's a pair of like terms going on that diagonal, and here's a pair of like terms going on that diagonal. And the others don't have matches, so the negative 14 comes along for the ride. Negative 12v and negative 35v on that diagonal there give us negative 47v. Negative 30v squared and 28v squared come along on that diagonal to give us negative 2v squared. And then the 24v to the third is by itself. So again, we've done all the same work, we've just organized the calculations in a different way. By the way, has anyone seen a table that looks like this before?
Yeah. Lattice.
It's a lattice. Where do you learn it?
Happened in middle school, I think.
There we go. So this is totally a generational thing, by the way. Part of what we think of as the, quote, new math is a way of getting away from some of the older algorithms for how to multiply multi-digit numbers, for example, and introducing algorithms like this one, that if you apply it to digit arithmetic, you can then apply the same algorithm to polynomial arithmetic later on, which is why I think they started teaching how to do this lattice multiplication in the earlier grades. So I think the Common Core is hanging on to some of that stuff, so lattice multiplication is going to still be around for a while. But I know when this first started showing up in, you know, 3rd, 4th grade, whenever you learn how to do this stuff, a lot of parents kind of freaked out because it looks completely alien compared to the original method. But I think the benefit is that you can kind of more clearly see what's multiplying by what to give you each of the terms that go into the product that you ultimately get. And the benefit is that you can use the same algorithm for polynomials as you use for multi-digit numbers. So whichever of these connects the best with you, whichever one you want to take away, will definitely work for you.